Welcome back from the weekend, and this is Talks. We have it most weeks when school's in session. Maybe in the summer we'll take off a month or a little bit more. The talk goes until about 2:20, 2:25, and then we have cookies and sodas out in the hall, just to allow people to get to know the speaker. I will typically turn on the microphones in front of you, so now the green lights are on. And Richard, who's going to be speaking today, likes people to ask questions, so that's a good thing, I hope. But rattling your keys on the desk will be noticed by everybody. So depending on how you feel about that, that's could be something you decide to do. In any case, we have this talk series, and it's on the web. You can go to just search for TOCS and CMU. You'll find a legacy of probably 80 talks given by people almost as exciting as you. And there'll also be people out in TV land watching and maybe asking questions during this talk. Richard comes to us from SRI, where he spent probably 35 years at least.
40 plus.
40 plus, and I've been working on cutting edge AI technology all along. Went to CMU long ago, graduated in '69, I think, with a PhD. Yeah, and I got to work, be around all those greats that were there. But anyway, theorem proving kind of stuff and kind of a mathematical side of AI has always been part of what he's done with his interests at times with nowadays it's kind of bringing it all together with domain expertise, planning, language, and theorem proving, right? So that's kind of, but those themes have been throughout your career as far as I can tell. Anyway, so I think it's exciting to have you here today, and from there I'll let you just take it. And be interested to see.
All right. Thank you, Ted. So this is work about getting us to be able to talk to computers in English, the way they do in Star Trek. And I mean, this isn't a new goal. In fact, I think it's probably one of the original goals of AI research was to be able to use English as your way of talking to a computer. But it's something that isn't done that much now, at least not in the way we originally visualized it. And I think the reason for that is that it turned out to be harder than people thought. So there's been a certain backing off and trying to work on more tractable subproblems that are more likely to be successful. So one approach is to take a subset of English, which is more manageable, unambiguous, easily parsed, and use that as your version of English that you talk to. The trouble with that is that it's hard for the human speaker to know what's in the language and what's not. And then there are the statistical approaches, which are like done by Google and by Watson, which I mean, Google is incredibly successful at what it does, but it, as you probably notice, it's not sensitive to differences between in word order and subtleties of it may not be doing just bag of words matching anymore, but it still there'll be it doesn't pick up the nuances of the question that you have in mind. So what I'll be talking about now is sort of good old-fashioned natural language understanding, where we really want to understand the question exactly and get exact answers, not documents that might contain the answer, but precise answers to the question. And because this is a hard problem, we're making it easier for ourselves by restricting the subject domain. So we're allowing, we're looking for full full English, English, any English structure is our communication language, but we are restricting ourselves to a particular structured domain, and we're getting answers from structured data, databases and structured data, not unrestricted text. And the particular area that we've been looking at most recently is the area of HIV drug resistance. And part of the reason for that is that it's a important and crucial problem. It's something where there's very good structured data to get answers to questions from, and we can get NIH support from the National Library of Medicine for doing it. Now, this picture is a picture of the city of Quadri, which is a city in Italy. Actually, we thought up the name for the project before we knew there was such a city, but it's very appropriate that Quadri has a bridge in it that you can see in the picture, and the bridge is called the the Infinity Bridge. That's the name of the bridge, and the project is kind of a bridge because we're trying to make a bridge between the English language question and the answer that's deduced from the data. And when I say we, I'm working with a team of people. I'm just the logic end of the team. There's the natural language is done by people from PARC, including Cleo Condoravdi, Daniel Bobrow, and Kyle Richardson. Now, PARC developed a system that was licensed to PowerSet, and they used it to parse the entire Wikipedia and presumably answer some questions from the Wikipedia. So it's a very very broad. It accepts a very broad. There'll be something that'll throw it off, but it accepts a very broad subset of English, very unrestricted. Anything that could be in the Wikipedia. Then there's me doing the logical, the reasoning part, and then the domain expertise is provided by people from Stanford. There's Amar, who is an access to databases expert, especially temporal databases. And there's Bob Schaefer and Soo-Yeon Ri, who are experts in the AIDS domain, and they have developed the HIV drug resistance database, which is our primary source of structured information. Now, the drug resistance database is it's very nice. It's a very well designed and well thought out database. It has clear structures in it. It has patients, regimens, which patients go from one regimen, and then if that doesn't work, they'll switch to another one. Each regimen has a combination of drugs associated with it. Then there are various measurements. There's measurements of viral loads. Having a high viral load is bad. It means your disease is active. And then there are genetic tests which can tell whether the virus has mutations in it. And mutations are important because you can develop resistance to an effective drug by having the virus mutate to be able to survive in the presence of the drug. So our target audience, although ultimately we are thinking of developing systems that are open to patients, so far we've been thinking about physicians and researchers as being the target audience, and that influences the kind of vocabulary that they're likely to use in asking questions. And we're assuming that they are not knowledgeable about the data resources available. They haven't used the database. They're not familiar with the interface that's provided, and we want to make it as easy for them as possible to get access to the data, because there's a barrier. Most researchers are not willing, if they have a question. They're not willing to learn the interface for all the databases that they need. We're assuming not that they'll eventually will have not just one database, but many databases which are possibly overlapping, possibly conflicting information. And we're looking at answers to questions where the answer is not, it's not a simple lookup. It could be something that you have to deduce or compute from answers that are existing in the database. So you may need to combine several pieces of information to formulate an answer to the question. So here's a sample question. What patients on a tripla is a drug combination, what patients on a tripla exhibited a high viral load? This is a simple question. High viral load is bad. The chances are that every patient is going to have a high viral load at some point, otherwise it wouldn't be patients. So this gets our approach is a logical approach where we take the question and parse the English and translate it into a logical form, which is a logical sentence that says, in this case, there exists a patient such that the patient has a regimen, so and so, and I didn't give the whole logical form, but it's you're proving the existence of things that you're trying to find. You're trying to, by proving the existence of patients, you're trying to find. Yes.
Yeah. What are the advantages of a theorem proving approach rather than say, kind of a more heuristic approach?
Well, the advantage is that in the best case, you can use declarative information in ways that you didn't anticipate using, and you can extend the knowledge by adding new logical sentences without having to reprogram it. So you're using very general reasoning to from declarative information rather than things that are hard programmed. So in the approach, we send this to a theorem prover. In this case, the theorem prover SNARK that's been developed at SRI, which proves the theorem and extracts an answer or multiple answers from the proof. So you might get a patient, Mr. A, and then another patient, Mr. B, and so on, who satisfies the conditions of the theorem. And the proof goes on in the presence of a theory, which is a theory of the subject domain, in this case, HIV drug resistance. So it has axioms, which are sentences written in logic, declarative sentences written in logic, which define the concepts in the query language. They define the capabilities of the data sources, and they provide whatever background knowledge is necessary to link them together. So we have a theory of some 400 axioms, which is not complete yet, but it's still growing, that provide this sort of information. And it's a sorted axiomatic theory, so the things, I'll talk about it more, things have sorts in them. And it's not dependent on any particular data source. So the concepts in it are not specific to the Stanford database, for example, but they're things that you would use in any HIV, accessing any HIV database. The concepts are independent of the domain. So here's an example of an axiom. We say a measurement is I didn't mean to do that. A measurement is a high viral load if it's greater than 4 on the log scale. So you could give an absolute measurement, but if you take the log of the measurement, it should be, if it's bigger than or equal to 4, that's regarded as a high viral load. So this is what we mean by high. And having this axiom in the system, in the theory, means that someone can ask a question looking for patients with a high viral load, and this ties it in with the database, which doesn't say whether it's high or low, but it just gives numbers. So it's an example of tying in the kind of abstraction that, or approximation that people use in asking questions with the numerical and quantitative stuff that's in the database. Yes?
Are you distinguishing between what you're calling an axiom and an assertion?
No. No, I'm using them interchangeably. Right. So, I mean, so in some cases, axioms will be things that you could possibly prove from other axioms, and we don't care about that. And so we don't care that they're independent or that they're basic. We sometimes add new axioms just to make the proofs faster. Okay, now the challenges in using natural language as our interface language are, well, one is that the language of that the person uses in formulating the query is typically different from the language used by the designers of the database. They may, the question asker might use one phrase, like someone might talk about a regimen, and someone else might talk about a treatment. So they're more or less the same. Or treatments are more general than a regimen, but you could use either one. And, what the database uses, the database tends to use regimen, but the person might use treatment. Then there's the qualitative versus quantitative, like the high versus for example, for viral load. There'd be approximations, like someone might talk about something being in about 24 weeks. Now that could mean 23 weeks, 25 weeks. You don't mean that it has to be exactly 24 weeks to the minute. Another problem that's often talked about is that English is highly ambiguous. So anything that you say in English is likely to be able to be parsed in many different ways. And we as intelligent listeners don't notice that because we have enough domain knowledge to know which one the person means to say and to throw away all the others without even realizing it. But the computer gets to see all those parses that we don't even notice. And then the stuff about English subsets I already mentioned, so I won't say it again. Now, the mapping, we do a mapping to from English into symbols. Like when we say patients on atripla, we actually expand that in the translation process using domain knowledge. So part of the if there's anything in our hypothesis, it's that by using subject domain knowledge, we can get overcome many of the problems in using English as an interface language. If you know what the person is talking about, you have a much better chance of understanding what they're trying to say. Like when we talk about patients on atripla, what we really mean is that the patient has a regimen, and the regimen has this drug combination, atripla, and this is something that the system can, even though the person hasn't mentioned a regimen, we know from our domain knowledge that the regimen is there, and that's what. And when we look it up in the database, the regimen is the way we're going to find out what drugs the patient is on. Now, so even this has ambiguity that we might not notice. Like when we said patients had a regimen with a tripla, it could be that the right interpretation, the one that's intended, is that a tripla modifies the regimen. So when we say a regimen with a tripla, it's a kind of regimen, a regimen that contains a tripla. This is what we mean. But it could also mean that that this tripla has something to do with the way the patients have it. So to switch domains a little bit, if I say I had a martini with an olive, that means that the martini has the olive. So the olive is sort of like part of something, telling me something about the martini. Whereas I say if I had a martini with Olivia, then Olivia is not part of the martini. Olivia is part of the having that I'm doing. So it takes domain knowledge to know that when I say the olive, I'm talking about the martini. When I'm talking to Olivia, I'm talking about someone I'm having the martini with. And domain knowledge tells us that it can't be the second interpretation because Olivia can have a martini, but an Olive can't have a martini. So that's something that you just need to know that fact about the world in order to understand which interpretation is meant. So our approach to ambiguity is to take type or sort information from the domain theory and use it to discard parses from the question that are syntactically plausible but semantically meaningless. And because we know that a triplet is a drug combination, we know that the regimen can have a triplet, but a triplet can't have the regimen. Whereas if it was something like every day, the patient has a triplet every day, that has something about the having is the everyday, not the regimen itself. Like a more complicated question, like find patients who had a high viral load after 24 weeks on a regimen with a tripla. This turns out, if we just feed it to the parser, we get 62 different interpretations of this sentence. And if we just use the method that I was telling about, using domain knowledge to rule out things that are semantically meaningless, we get one reading, the one that we intend. Now, that doesn't mean that we always can deal with all ambiguities, but it's a tremendously powerful tool for dealing with ambiguity, using subject domain knowledge. If we do get ambiguous sentences, there are some approaches. One approach is to ask the user which one they meant, which is something that we that's like the first stab. And then the other one is to actually go ahead and generate answers to the, if you have more than one interpretation, generate answers for each one, feed them back to the user and see which one makes sense. Often, if a question has 0 answers, the chances are that's not what the person meant. Or if everything in the database turns out to be an answer to the question, it's also probable that that's not what the person meant. So those are heuristics for throwing away bad parses. Now here's an example. I'm not going to explain it, of the logical form that comes out of that question: find patients who had a high viral load, etc. And it gets expanded. So it talks about the regimen, which is not mentioned. Oh, it actually, here it is mentioned in the sentence and so forth. So it has, now these quantifiers, this X stands for exists. So these are, I'm proving there exists a patient, I'm proving there exists a regimen having all these properties. Now, once we've parsed it and constructed this logical form, what we do is we translate it back into English and feed it back to the user. And this is so that they can see how we've understood what they've said. And there's still a chance, even though we've thrown away all these ambiguous things, there's still a chance that the parse is wrong, and that we have interpreted the sentence in a bad way, and that we should give the person a chance. Now, the English that comes back is going to be a lot wordier than the way the person asked the question, but it's in English, it's understandable, and they can see if we've taken it to be what they meant, and if we have several alternatives, they can throw out the one that they don't like and give them a chance to rephrase it. Now, the theorem prover is the theorem prover SNARK, which is developed by Mark Stickle at SRI for, it's a 25, 30-year-old theorem prover. It's a very, it was used at NASA in the Amphion system, which was for program software composition, and it's been used in a variety of different projects, both at SRI and outside of SRI. It's a first-order logic theorem prover. It's sorted, so it has types. It knows certain things are regimens, certain things are patients, and it classifies those syntactically. It has capabilities for extracting information to queries from a proof. It has special facilities for temporal reasoning, which turns out to be important in the medical domain because the regimens have time extent. We have dates for when they start and when they end. And it has a mechanism called procedural attachment, which turns out to be crucial for accessing data. So what is procedural attachment? Yeah.
Just as you're kind of in the same line as question, as you're going forward, it's helpful if we can kind of tell what did theorem provers 10 years ago not have that we have now, or what's our response to the people that are pretending that planning is not even worthwhile and we'll do everything statistically.
Well, theorem provers have slowly and gradually been increasing in power. Part of that is because machines have been getting more powerful, but also techniques have been getting more sophisticated. SNARK is especially good at being focused on a particular subject domain. You can give it heuristic information, which will make it go faster in that domain, although not necessarily in other domains. I know, like when I first started, there were huge prizes given for the first theorem that first open theorem to be proved by a theorem prover. There was like $1 million prize for who could prove an open conjecture, what theorem prover would be able to prove, and it was regarded as something that was quite difficult and likely to not be done. Whereas now it's routine that open questions are solved by theorem provers in the mathematical literature, at least. It's very like the Robbins conjecture, which was a problem that Tarski had dealt with in the 20s, that was open for ages, was solved by an Argonne research laboratory theorem prover, and the proof was only a page long, I believe, but it was something that no person had been able to find. It was something conjecture in Boolean algebra that simple to state, but
What was the name of that again?
the Robbins conjecture. It was after Herbert Robbins, who was the one who first conjectured this. Is this axiom an axiom for Boolean algebra? It's a simple enough thing to understand, but the proof was something that was very difficult to find. Okay, now procedural attachment is something that can link symbols in the axiomatic theory. The axiomatic theory is a bunch of axioms. Certain symbols in the theory, like patient has regimen, can be linked to things that you can look up in the database. So if you're given a patient, you can find out, look up in the database, what regimens does this patient have? So that's a procedural attachment that lets us take a symbol in the theory and look up stuff in the database. And so when that symbol occurs in the search for a proof, the database is invoked. It returns an answer, usually a bunch of answers, like the patients in the database, and it feeds them back to the theorem prover. The theorem prover will start a different branch in the search space depending on which regimen we're talking about, and so the proof resumes using information it got from the database. So so it makes we don't have to give all the information in the axiomatic form in the logical theory. Most of the information that the theorem prover uses is actually stored in the database. The only stuff that's in its theory are sort of the choreographic information that tells us how do you look up this information in the database? Can we get it from the database, and in what form do you have to ask the question? So it lets us expand the axiomatic theory based on what's in the database. And so we have, like, patient has regimen is linked to the Stanford HIV database, or patient has a test of viral load or genetic test. Those things are linked to the database. But we can as well use other sources. There are European sources. There are other American sources for HIV drug resistance. And then there's certain information is not in the database at all. Like they use a particular name for each drug. but the person who's asking the question is likely to use common names or commercial names, which are not in the database. So we have another database, an NIH database, that tells us what the various names are for the drugs that could be used. Now, usually there are multiple answers to a question, like many different patients might satisfy the conditions of the query. And so each answer comes from a different proof. The person may want a visual display of the information, like if it has to do with what regimens a patient has been on, we may produce a visual display. Now, fortunately, there's another project going on at Stanford involving some of the same people for visual display of HIV data. So we tie in with them to provide displays that will answer the question when that turns out to be appropriate. And we're doing evaluation of the system using some of the questions that have been developed to evaluate this visual display system, which is called Suite Info. And here's an example of the kind of display that Suite Info produces. We don't do this ourselves. We just send information to Suite Info, and they come back with these displays, more visual than the text. Now, one thing, once we've produced an answer, the person who's asking the question might want to know, how did we get this answer? They might want some validation. They might want to see what information was used, what the sources were for the data that was used in getting the answer. And so what we do is the proof from which the answer is extracted also provides a validation of that answer and an explanation, and the procedural attachments that are used provide information about what the sources of the answer are. So what we do, this isn't done yet, but this is relatively straightforward, is we construct an English paragraph, not explaining the reasoning, which is usually straightforward, but we provide English paraphrases of the axioms that are used in the proof. And that turns out to be enough in most cases for the person to understand where the answer came from. So here's an example for the question that I was talking about. Here's an example of, this is done by hand because we haven't implemented this yet. A tripla is a drug combination of blah, blah, blah. This is from the procedural attachment where you look up what a tripla is. And then we talk about times being near each other. We want to say close to 24 weeks. Times are near each other if they're within 3 weeks of each other. That's sort of liberal, but that's what we're using so we get more answers. The duration of a time interval is the difference between its finish time and its start time. This is a basic fact about the world, but it tells us what we mean by duration, and so forth. So we have an English sentence which is, and we do the sentences exactly in the order in which they're used in the proof. So this gives them a sort of coherence that you wouldn't expect from if they were just given at random, because the order follows the reasoning the theorem proof used in producing the answer, and it tends to have some coherence. Now, the current phase of what we're doing involves complex queries which have multiple questions. So it's unnatural that a person is going to give a complex query, just sit down and think of this complicated question and come out with an English paragraph that represents the question. So what we do is we let them give the question in stages. So first you might say, find patients who had the high viral load after 24 weeks. And then you might see some patients that correspond to that. And so you might, that might give feedback whether the person's on the right track. Did they get answers that they are surprised with? Were they not getting answers they expected? It lets them change the question if they're not happy with it. And then you go on further. They say the patients exhibited the mutation M184V near the end of the regimen. So this is like a filter on you're throwing away now patients who don't have this any sign of this mutation. They didn't, either they didn't have a genetic test, or they did and it didn't show the mutation. And then there's a third part to the question. The patient switched to a salvage regimen with boosted EHV. Now this is turns out to be a more subtle kind of question, because there's no, we talk about the salvage regimen in the third part of the question. There's no mention of the salvage regimen in the first two parts. We mentioned a regimen, but it turns out that the salvage regimen is not the same as the failing regimen. The salvage regimen is a regimen that comes after the failing regimen. You have a high viral load. That means the regimen is failing. The salvage regimen is the one that you switch to, and you never leave the patient with the high viral load. You switch to the salvage regimen. So this requires some domain knowledge to know that what the person is talking about. It's like if someone tells me a car was speeding by, and then you say the horn was honking loudly. You know from domain knowledge that the horn, when I talk about the horn is the horn of that car that's speeding past. Even though there may be other cars on the block that also have horns, you know from domain knowledge that the horn is the horn of the one that I mentioned in the previous sentence. Same with the salvage regimen. So here, the way we do these multiple questions is we actually prove a sequence of theorems. So when I say, find all patients on a failing regimen for at least 30 weeks, I prove one theorem: there exists a patient having this failing regimen. So I may get multiple answers to that, because there'll be many patients who have a failing regimen for at least 30 weeks. Then the second part is the patients exhibited the mutation M184V. So then I'll have another theorem which says there exists a patient, because I'm finding patients still, that exhibiting this high viral load. And what it does is it knows the English language tells us that the patients in part 2 are the same as the patients in part 1. So I'll prove one theorem in which patient 2 is Mr. A, because Mr. A is one of the answers to the first part. And for the other answer, where patient 1 is turned out to be Mr. B, I'll prove a theorem in which patient 2 is the same as Mr. B. So for each answer to the first part, I'll generate a new theorem for the second part, which will be sent to the theorem prover, which will come back with answers to the, and it'll throw out, like if Mr. A doesn't have the mutation, it'll just throw out that answer, and you'll get Mr. B, but not Mr. A. So this is the current phase of the work we've been doing, the multiple questions. We also are interested in extending this now to other domains, like the database people we've been working with at Stanford have connections with people doing breast cancer work. And so we have domain expertise in breast cancer, both at Stanford and at Palo Alto Medical Foundation. And part of the new project involves providing healthcare information to patients. So although we've been dealing so far with physicians and researchers, the new phase of the project will deal with patients who may want information. So this is.
Aren't you expecting to see very high variability in patient questions, and even things where patients say, you know, what about whatchamacallit?
Yeah. Well, first of all, they know they'll be typing into a machine. It's not speech, it's typing. So they may be more formal in typing than they would if they were asking a question to someone they knew as a person. But we do have sample questions that they have been themselves already assembling lists of questions that are actually asked by breast cancer patients. So that'll be our starting point for doing the. Now we have done some experiments with switching domains, and it turns out that of course, you have to have a new axiomatic theory for the new subject domain. There's no getting around that, but there's a lot of things in common, like temporal information tends to be the same source. So a lot of the work we've done for the HIV will carry over to the breast cancer. And the natural language is quite good at switching over. We tried moving the natural language over to an intelligence domain having to do with terrorist attacks, and it turned out that that was quite a bit faster than developing
So in creating these axiomatic models, what kind of automated tools are there or can there be?
Well, that's something that part of the new project involves expressing axioms in English and having them translated into logical form, which is similar to taking the queries in English and translating them into logical form. So that's something that we feel is not a big step. There's more emphasis on logical connectives in the axioms than there is in the queries, but it's something that it's a logical next step for us to take. But I bypass Thomas.
I have a question. You need to have a boundary between what the theorem prover does and what the databases do. I was thinking, I don't know if this was the approach you took, or there's a different approach where you synthesize a program, which then is a database kind of program that does joins and filters or whatever.
Yeah, that is not what we're doing. That is something that we might do, and eventually we might have to do it. But what we're doing now is just looking things up in the database and as the proof is in progress. So instead of writing a program and then having the theorem prover stop, then running the SQL program, say, we're sort of letting the theorem prover be our database language and having it go out. Now, so far we haven't dealt with the efficiency problems involving large amounts of data. It could be that we'll need to go onto your approach if it turns out what we have is not efficient enough. Like in another project involving molecular biology, we used comparable sized databases. Like the database that we're looking at now has like 5,000 patients in it. In working with E. coli has about 5,000 genes. So it's a comparable size database, and for big questions, it could take a minute to answer them, which is too slow for Google, but for the kinds of if it's something that would take a day to do by hand, it might be worth waiting for a minute to do the answer. But so if we can do it in a minute or two, we'll be happy in the new database. Otherwise, we may have to take an approach of actually constructing the program, which is more complicated, especially if there are loops in the program. It might mean induction proofs, which are more challenging. The proofs we are doing now are very we can do. They're fractions of a second typically, and not challenging with the theorem prover. Whereas the proofs you're talking about would be more challenging. Here's an example of the when we're extending the database in English. We might say a viral load is high if and only if the log of the viral load is greater than or equal to 4, and then we would get the axiom that we saw before about the high viral load. This is something we haven't done yet, but it's something it's plausible that this is in the order of complexity of stuff that we've been doing. Yeah.
Question on the axioms. How do you validate them? Some of them seem pretty arbitrary, like near is 3 weeks.
Well, that isn't something that we can't say it's right or wrong to say near is 3 weeks. It's a matter of what the person means. So
right.
For something like near, we haven't done it yet, but we can ask the person we can say, when we say near, we mean something like this. We can say this in English.
Yeah.
And they can either accept that, or they can say, no, when I say near, I mean.
And the same thing with like
And
high
same-
viral load. You
High
could say,
viral load,
I
yeah.
want 5, not 4.
Yeah, I want five. So something like that is a natural for feeding back to the user with a question. When you say when we say high viral load, we mean bigger than 4. Is this okay? And,
Yeah, you could do that.
yeah,
Okay.
and it's not something that we can't prove that a high viral load is bigger than 4. It's something.
Right.
It's just a matter of what the word means to the person, and different people may mean different things.
Yeah.
We don't do it yet, but we may have profiles where this person says hi, they mean this. When this
Right.
person says hi, they mean.
Do you classify the axioms as more opinion versus more common sense, so that when you print out the proof, you could maybe delete the ones that are obvious?
Well, in giving the explanation for the proof, there's some things we print out and some things we don't.
Okay.
Like a week is 7 days.
Yeah, that's
Is
what I
something
mean, stuff like that.
we
You
don't
need to
want to
tell
print. We
people.
don't want to make that be part of the explanation, because
Right.
it's first of all, it's so obvious that the person already knows it,
Right.
and it's boring to read it, and it hides the stuff that really is more controversial. So that doesn't have an explanation.
So you do
generally.
indicate which ones should be printed out.
Some of them we indicate are not to be
Okay.
printed. And that,
Thanks.
is,
I'm kind of excited about that 7 days example. It seems like there's a lot of things like near and viral load that should be generalizable, right? That we should be able to make, more use of in other domains if we define it in some way that where the abstraction carries. Do you have, what do we do moving forward so that we'll have a question answering system that'll work across domains and won't get confused by viral load being this high viral load being bad, being really something for HIV and quite different for streptococcus or some flu.
well, we did some thinking about that, which is not in the system, all of it yet. But like when you say, if someone says about 100 weeks, they could mean 90 or 110. If they say about 99 weeks, they probably mean between 98 and 100. When you give a very precise number and say about 3.4, you don't want 6. Whereas if you say about 4, you might accept 6. So there's certain things like that. The way you phrase the question could have something to do with the about. And of course, with about also is we do it with percentage of the size. So about 100 weeks is a bigger. Should be. It shouldn't be like 3 weeks. If we're talking about something that's 2 weeks, saying within 3 weeks is not close enough. So what we have now is obviously too coarse.
99 versus 100 is a much more exciting example.
Yeah, and that's domain independent. It doesn't have to do with HIV. It has to do with what we mean by approximation. So we'll do something better about that later on.
Do you see any advantage to using a cycle-like system for these universal axioms?
Well, we have looked at psych axioms in the past, and we find them. We've taken some axioms from them, but most of the axioms in the system are not in psych. They're specific to the medical
It
domain.
seems like some of the time axioms, and there's levels of generality.
Yeah, actually, Sykes' time turned out to be, first of all, their theory was inconsistent, and SNARK is very sensitive to inconsistency because it spends all its time looking for inconsistency. And when it finds an inconsistency, it's very happy because it thinks it's found the proof. And so they had their idea that 2 time points could have nothing in between them and still not be the same, which is okay if you had integer time points, but it's not really true in the real world. However close they are, they have this something midway between. And when you give that to SNARK, it gets a contradiction right away. And I told the psych people about that, and they said, well, they knew that, but their theorem prover doesn't find it, so it wasn't a problem for them that they had this inconsistency, and they were more inconsistency tolerant than we were. So you have to look axioms in the eye before you import them.
Sort of follow on to that question, it seems like you're operating at the level of what the psych folks call the microtheory level.
Yeah, this is sort of it's not a small microtheory, but it is a very focused.
Yeah. So the question then would be, did you have to invent your own upper ontology, or do you use someone else's, whether it's Sykes or Sumo or?
There isn't much upper ontology there. So
like time, I guess.
Yeah.
But
what's that?
Time
is, well, SNARK has a very good its own system for time. It has time points and time intervals. So it deals with it has a version of the Allen calculus, which the Allen calculus is a temporal reasoning calculus that deals just with intervals. Now the SNARK's version, which Stickle developed, has both time points and time intervals, and it distinguishes between them and knows the relationship between them. The Allen calculus has 13 temporal relations between intervals. SNARK has 25, because that's how much it turns out. Because you do interval, you do point, you do point. So
you rolled whatever upper ontologies you had to make this thing work.
Yeah, so there is an upper ontology in there, but it's a bit more expressive than what was out there. Thank you. Yeah.
Have you heard of something called Wolfram Alpha?
Yeah.
How does this, I guess, parsing method compare to that one? Because they seem to perform very similar jobs. How do like the methodology of like going through like the wording of a query compare to like Wolfram Alpha?
I don't know exactly, but the PARC people have spent a lot of effort on doing things like the interaction between temporal operators and logical connectives. So it can tell the difference between, like if I look for a patient, not all of whose regimens contain a tripla, that's different from finding a patient, all of whose regimens do not contain a tripla. And you can get different answers depending on which question you ask. And they are pioneering in doing this kind of English parsing. And I bet that Wolfram can't do it. Now, I didn't try, but I bet you that Wolfram can't tell the difference between them. I know Google certainly can, and I would suspect that Wolfram isn't going to be able to do that kind of thing. And for the database application that we're talking about, those sorts of things are critical. You know, you don't want to confuse those two. You're not happy getting data that satisfies one of those questions when you meant to ask the other one. It's just bad. But no, Wolfram is, I think it's a very impressive system, and I've seen very impressive results from it. What you need to do is try it out yourself, though, because the way that, and it's true of our system too, the ones we choose to demonstrate the system are going to be the ones where it works and works well, and they're hard. And often you'll find that if you ask something a little bit different, something that's not more complicated but equally complicated but a little bit different, it's not going to work. So you can't just go by something that is they say they show you this impressive example, or we show you this impressive example. What you have to do is take the system, and our system isn't going to do it yet, but this is what our goal is, to have someone who hasn't designed a system sit down and ask a question in a natural way and have them get answers from it. That's where we're headed, and I bet you that it doesn't take long before you fool Wolfram.
So just saw something on the web then with Wolfram Alpha having trouble with until, and it couldn't parse the word until time expression that well.
Yeah, I tried one of those systems. It wasn't Wolfram Alpha, it was another one. I asked it, did the Civil War occur before World War I? And it didn't know. It was something. It knew lots of other things about the Civil War and World War I, but it didn't know that the Civil War occurred. If you asked it that, it wouldn't know the answer.
So just for the student, there's some students in the room. What would you say about studying logical AI for them, and then second question is how do you feel? Did the experience of Jeopardy with Watson change any of your feelings about any of these things?
Well, I was impressed and surprised that Jeopardy did so well, and I went to Chris Welty's talk, and he seemed impressed and surprised that it did so well also, even though he worked on the system itself, and he made it seem as if it was quite lucky that it did win, because it was anyone's guess whether it did and what it has is it has lots and lots of knowledge, much more knowledge than any of the but it does not really understand the question. So it's lucky if its interpretation of the question turns out to be the one that was intended. It doesn't have very much common sense reasoning. It didn't know. It wasn't sure exactly whether Toronto was in the United States or not. There was some evidence that it was, but some evidence that it wasn't. It didn't know that a person with a wooden leg, that there was anything unusual about a gymnast with a wooden leg. It knew that one of the gymnastic contestants had a wooden leg, but it didn't classify that as an unusual thing. So when they asked what was unusual about the 1911 Olympics, it knew that this guy had a wooden leg, but didn't know that that was anything to be remarked on. That it was out of its domain knowledge.
Would you expect that your kind of approach would have caught those things better, or
Well, the problem with our kind of approach is that you need to have axiom. You have to codify it by axiom. So you would have to have an axiom that normally people have. So that's our approach works on. You have an axiomatic theory that focuses on this domain. Now, if we had a gymnastic theory, it would be we would have done better than them on that particular theory, but we would not have to get something of that breadth would mean having lots and lots of different theories and melding them together, and presumably these sub-theories would be developed by different groups, different people, and then the melding together would be done by the kind of people who write the thesauruses and dictionaries, or the people who wrote BirdNet.
is that a world you expect?
Well, there have been people who've done that in the past. If it's worthwhile, some people. WordNet took 3 people 15 years to do, which is a lot, but also it's not that much if you consider it on the level of the size of most DARPA projects. It's a small project for DARPA, and think of how useful it's turned out to be. WordNet is a computer dictionary that is very commonly used. It's used by our project, and used by. And also, if you do Google Dictionary, you'll get the WordNet definition.
Any last question, or should we adjourn to the cookies?
All right.
So,
Yeah, sure. Shall I leave my machine?
no, bring it with you. Let's depart, because what happens is.
Okay.